Why, hello! It's Miss Heaton signing in to talk about equilibrium a little bit more. We are going to dive into some pretty heavy algebra today, so hopefully you've got your calculator handy and your math hat on. Today we're going to be talking about what to do if you know the value of your K and you know a little bit about concentrations, but you're asked to find how much the concentration of different chemicals are at equilibrium. This is a little bit more intense than the ice chart stuff. You're going to have to do a little bit more algebra. We are also going to be using ice charts to help us organize our thoughts, and we're also going to be using our KQ expressions. So here we go. This method's a little bit easier than some of the others that you will learn later, and so if you can do it, you'll want to do it. And it is the best thing to use when you have a square in your KEQ expression. And that will make sense a little bit later, but you may want to jot that down. When you have something squared over something squared and you can square root it to solve for x, that's going to be important. So here's the problem we're going to tackle today as our example. We've got a mixture of H2 and I2, 1.5 moles of each, in a 2-liter flask at a certain temperature. We're given the reaction, notice that it's at equilibrium, and this is the KEQ value, 79.5. We're going to try to find the concentrations of everything at equilibrium. The first thing we'll want to do is figure out what we're starting with. It looks like we're given number of moles, but we probably want to have molarities because that goes into our KEQ and our ice chart. Remember, molarity is moles over liters. So molarity is 1.5, and we've got 2 liters, so that would be 0.75 molar. And that would be of our H2. And since we have equal moles and equal volume, that would also be our molarity of the I2. Notice that these are initial amounts because this is what is placed into the flask. So when we do make our ice chart later, those will go in our initial row. The first thing you'll probably want to do though is write your KEQ expression because you're pretty good at that by now, right? We'll put products on top. So our product of our reaction is HI, hydrogen iodide, and it's a gas, and there's a coefficient of 2, so we will need to square the HI. And then our denominator will be H2 to the first power because its coefficient is 1, and I2 because its coefficient is 1, so it's also to the first. And we could maybe write down that that's going to equal 79.5, so we don't forget that. Remember that that constant could change at a different temperature, but for the problems that I give you, the K value will stay the same throughout. Our next step is going to be to make our handy dandy little ice chart. Remember, ice, ice, baby. Ice stands for initial, C stands for change, and E stands for equilibrium. I'll write that in. Initial and change. We'll also want to rewrite our equation. H2 plus I2 is in equilibrium with 2 HIs. Let's change colors for clarity's sake. Remember back up here we calculated what our initial or starting concentrations were. We had 0.75 molarity of H2 and 0.75 molarity of I2. HI was not mentioned at the beginning, so we can assume that we had 0 of that at the beginning. Now, this change row, the next step, is where a lot of people get confused. And so I need to tell you one more thing about this. Typically, you will be losing your reactants to make products, and that's actually what's going to happen in this case. But it is possible that you would have too much products and you need to shift in reverse to make your reactants. So you should probably do a quick Q calculation using your initial amounts and your KEQ expression. So you do your product squared over your reactants. So that would be 0.75 and 0.75. Turns out that Q is 0 here. Q is obviously less than our K value of 80. So that means it's going to shift in the typical direction. It's going to shift forward. And so we can do our change row the way that we have been doing it. The coefficient in front of H2 is 1, so every time we do the reaction x times, we're going to lose x H2s, we're going to lose x I2s, and then since HI is our product, we're going to make 2 HIs because their coefficient is 2. So we could fill in our equilibrium row. That would be, let's see, that would be 0.75 minus x, 0.75 minus x, and then 2x at equilibrium. We can then take those numbers and plug them into our KEQ because we don't have any additional information. In some of our problems, we were told at equilibrium you had this much HI or this much H2. They didn't give us that info. They're expecting us to know how to do some algebra here. So we will plug in our equilibrium concentration of HI, which is 2x. Remember that that will be squared. Sometimes people forget the 2 in their change row, or they forget it in their KEQ. It goes in both places. Then on bottom, we'll put in 0.75 minus x and 0.75 minus x for our hydrogen and iodide. Okay, this is where you're able to identify how to solve algebraically, and this is where the square root shortcut comes in. Because look at this, we could rewrite this as 2x squared over 0.75 minus x squared, because we started with the same concentration of both of our reactants. How handy is that? I love when that happens. So we could maybe rewrite this 79.5 so it's closer to where we're doing our work. And this is what we're going to solve. That looks like a weird letter. Let's change that. There we go. Okay. Now notice that the easiest way to solve for this algebraically is going to be to take the square root of this, because these are both squared, so if you square root it, we'll get rid of those squareds and not have to do like the quadratic equation or something crazy. Now if you do it to one side, you got to do it to the other as well. And so when you do that, you'll end up with 2x over 0.75 minus x equals 8.92. And you don't need to worry about the negative possibility in the square root because this is chemistry and we don't deal with negative substances, only positive. You can't have a negative concentration. From here on out, folks, it's just algebra, and so you'll multiply both sides by this probably, so you'll get 2x equals 8.92 times 0.75 minus x, and then maybe distribute the 8.92 in. You'll get 6.687. It is better to keep more numbers rather than cutting it off early. Save as much rounding to the end as possible because you are dealing with small amounts and even a little bit of rounding can cause you to get a very different answer. So we're just kind of do some algebra, get x by itself. If you do have questions about this process, make a little star by it, ask somebody in class tomorrow. But when you solve for x, you should get about 0.612 or 0.6124. Great, is that the end? We got x. Let's look back. I don't think so. It says calculate the concentrations of these things at equilibrium. So now we need to take our x value, go back to our equilibrium chart, our ice chart, and say, okay, when we plug in that change amount, what do we end up with? Well, 0.75 minus 0.6124 turns out to be about 0.138 molarity for our H2. We're going to get the same thing for our I2 because the x is the same, so that'll be 0.138 molarity of I2. And then for HI, it'll be 2 times x, so 2 times 0.6124, and that turns out to be about 1.23 molarity of HI. And that would be your answer. If you want to check your work, you can always plug these equilibrium values back into your KEQ and you should get a number pretty close to 79.5. It may not be exact, but it should be pretty darn close as long as you did your algebra and rounding correctly. Okay folks, that is the square root method. Remember that this is what you'll use when you have a squared on top, a squared on bottom, and you are solving for x. Okay, this is Miss Heaton signing out for now. Tune in next time for an exciting quadratic equation screencast. Later.